Welcome, everyone. My name is John Mullally, and I am the CPAS Communications Manager. And this position affords me the pleasure of working with and getting to know some of our wonderful scientists, like our guest speaker today. I'm delighted to have you attend the CPAS Seminar, Discovery Seminar Series, because CPAS scientists do everything from explore the ocean depths to fly into hurricanes to heliophysicists modeling coronal mass ejections and those who unravel the mysteries of the Arctic. And we want to share this with the public, the NCAR UCAR community, and our many colleagues at universities and agencies across the globe. Just to orient you, we are using Slido, so you will be able to post questions for our speaker. You will find access in the tab at the top left of the screen. So, speaking of the introductions and people flying into hurricanes, it is my pleasure to introduce Dr. Zorana Jelenak, an internationally recognized expert in satellite ocean remote sensing and extreme weather observations. Dr. Jelenak works with UCAR.CPAESS in collaboration with NOAA NESDIS, where she leads the development, collaboration, and operational transition of critical satellite ocean wind products used in forecasting and data assimilation. She has also logged more than 400 hurricane eyewall penetrations aboard NOAA's P-3 aircraft, more than any other woman in the world, combining direct in-storm experience with deep technical expertise and microwave remote sensing. Her work has shaped national decisions on data quality, product adoption, and operational readiness across multiple satellite missions. In recent years, she has been advancing frameworks for trusted AI-ready Earth observations to ensure scientific rigor in the commercial satellite landscape. Her career reflects a sustained commitment to delivering accurate, reliable data to improve forecasting and reduce the impacts of extreme weather. Today, Zorana will be speaking on In the Eye of the Storm, from storm force errors to gold standard science. Zorana, the floor is yours.
Thank you so much, Don. A very nice introduction. People often ask me how I ended up flying into hurricanes, and I can't say it was a childhood dream. I remember one year in fifth grade dreaming about becoming an astronaut, but not necessarily flying in Cat 5 hurricane. After finishing my PhD in New Zealand, I saw this advertisement and it was like written for me. It was like continuation of my PhD thesis. It talked about ocean winds, satellite science with operational impact. And it was for UCAR visiting scientist position within known as this ocean winds team. I might have written really good application since to my complete surprise, I did get a job. I joined the Ocean Winds team on the same day my firstborn turned 6 years, and next month he's turning 31. The team's mission then was as clear as it is now. We want to deliver satellite ocean products to ensure they are accurate and trustworthy for forecasters and decision makers, especially in extreme conditions that matter the most. That commitment to operations led the team to design aircraft experiment to validate these satellite measurements in harshest environmental conditions on Earth. If you were part of the team and willing, you could fly. So my first flight was on September 13th, 2003 into Hurricane Isabel. At that time, Isabel intensified at the Category 5 hurricane. So on my very first mission, I entered what we jokingly call Category 5 Club, something that many crew members waited decades to experience. I didn't have to wait. I was really hooked. There's something really extraordinary about being inside the systems that's powerful. You feel the intensity, you see the structural lack of it in the eye, and you know, most importantly, the data you are collecting will make satellites more accurate, forecasts more reliable, and communities safer. That first flight didn't just launch a mission, it launched a career. And today, I have a privilege of serving as a science lead for this team. Every member of Ocean Wind team is an exceptional scientist. But what makes it extraordinary is how we function together. The dedication, the wit, the willingness to challenge assumptions, and the collective problem solving amazes me on a daily basis. Individually, we are all strong, but together we transcend ordinary science. For this talk, I could have chosen to talk about our biggest successes, major campaigns, scientific breakthroughs, first of a kind products. Instead, I chose to tell a different story, a story about an integrity moment when we discovered an error. And I want to tell to all young scientists listening today that I choose that story because the real setback is not discovering an error. The real setback would be ignoring one. Storm force errors are inevitable in complex systems, but golden science is built in how we respond to them. So before we fly through science, let's step together into the environment I work in during the hurricane season. What I want to take you through is Category 5 hurricane, but Patricia was the strongest one in the East Pacific, and we flew through on board the P-3 aircraft. You will see the eyeball penetration, you will see amazing views in the eye, and you will see the violent ocean surface. What is important to remember that in all of those, we collect the data. So okay, I didn't see the movie. I hope you felt what we feel as we fly to it. What is important to remember in this video is that measurements we take with the instruments on board of the aircraft, as well as measurements we take on the board of the space, are not direct measurements. Those are indirect measurements. These instruments measure electromagnetic energy, and everything else is extracted from that. It's the interpretation of the physics, and interpretation only works if we truly understand the physics behind it. So what I want to talk first is about the instruments we utilize on board of aircraft and satellite to measure ocean surface, wind speed, and direction. One of those instruments are scatterometers. They are specifically designed microwave radar to measure near surface ocean wind speed and direction. The way these instruments work is like a flashlight. You transmit electromagnetic energy. It scatters in many directions on the ocean surface. And we measure the energy, only portion of the energy that is backscattered in the same direction as incoming radiation. The quantity we measure is basically the ratio between transmitted and received power. And as you can imagine, that ratio changes as the surface roughness and conditions in the atmosphere change. What we get from the measurements is something that we call radar, normalized radar cross-section. And if we plot the image of it over storm, it looks like this. Now, to go from sigma naught measurements into wind speed and direction, we need to understand the physics that models the dependence of the measurement to these surface parameters. Depending on that physics, we come up with the products. Now, what I want to show you, what I meant by these are indirect measurements. As I said, we need to understand the physics to go from the measurement to the product. And I want to show you an example of products that were developed from European Advanced Scattorometer, known as ASCAT. And
Zorana,
yes,
can you reshare your screen so that we can see the data that you are talking about? Thank you.
so this is example of how scatterometers measure the winds over the ocean, the transmitted pulse and the received pulse. And then the quantity that we measure, normalized radar cross-section, it looks like this on the image from which we derived near surface ocean wind speeds and direction. Let's look at the examples that will show what we need to understand when we talk about that these are indirect measurements. So we start with the basic measurement of European Advanced Scattorometer ASCAT, and we utilize three different algorithms to derive wind speed and direction over the extratropical cyclones in Labrador Sea. The first one provides the information that storm is the gale force wind. But if we apply different algorithm, we get the information that the wind warning category should be storm force winds. The third algorithm we applied, we actually get that wind warning that the storm reached the hurricane force winds. Now imagine the forecaster, if they have three different products in front of them, which one is right? These warning categories have real life implications on the sea. So in order to answer that, which one is right, which one do we trust, we designed NOAA NESDIS Ocean Winds Aircraft Experiment. This experiment has been flying from late 90s. We utilize NOAA P3 aircraft, and on this aircraft we fly two different instruments, but initially we started flying with imaging wind and rain profiler, which is double frequency, Doppler radar, and scatterometer. And we utilize this experiment to calibrate and validate all satellite wind measurements that were utilized in operations today. How this instrument operate? The radar that we have is conically scanning, and it's taking, as the aircraft is moving, it's taking measurements both from the atmosphere and from the ocean surface. Implementing retrieval algorithms, we can get information of the atmospheric horizontal wind profiles, as well as ocean surface wind speed and direction. Now, on the aircraft, we don't just have IRAP. This is the instrument that we specifically design and install on the aircraft. We have several different instruments that also measure wind. With different instruments, we get somewhat different answers, but there is only one truth. What IRAP is providing us is, as I said, 3D atmospheric profiles that directly connect flight level winds with the surface winds. But we have also the flight level wind speed and direction measurements. We have the drop zones that are drops occasionally through from the airplane. We have step frequency microwave radiometer, which is the instrument I will concentrate on today that provides near surface ocean wind and rain rate. We have tail Doppler radar that, like IRAP, is providing 3D winds, but with a much larger swath and a lower resolution. Ideally, all these instruments agree, but more often than not, they don't. And we utilize IRA because it's providing so many different type of measurements to bring all of them together and understand them better. But let's talk about golden science for measuring, golden standard for measuring ocean winds, which was step frequency microwave radiometer. NOAA acquired 3 different SFMR units and started utilizing them since 2006 in operations to impact hurricane intensity estimates. Data was assimilated in forecast models. Every single wind calibration and validation was done utilizing these measurements, not just nationally, but internationally. Many research publications are impacted by this data, and increasingly AI training data sets utilizing this to predict the intensity of the hurricanes. So for more than 20 years, this instrument has shaped our understanding of tropical cyclone intensity, but we discovered something was wrong. But before I show you what we discovered, let's understand how microwave radiometers measure the ocean winds. Microwave radiometers are passive instruments. Scatterometers are active, they send the pulses. Microwave radiometers listen, naturally emitting microwave radiation from the ocean surface, from the upward traveling atmospheric radiation, and also from the downward traveling atmospheric and cold space radiation that is scattered back from the ocean surface. Together, this signal forms the brightness temperature measurement from which we derive different surface or atmospheric parameters. Step frequency microwave radiometer makes observations at 5 different frequencies. This is an example of how brightness temperature of step frequency microwave radiometer changed during the inbound and outbound track through Hurricane Fiona. And you can see the 5 different frequencies spreading at some point or rising and lowering at other point. The spread between frequencies is directly impacted by rain. So from the spread of the frequencies, we retrieve the rain rate. From the slope of the brightness temperature, we retrieve the ocean surface wind. And we've been doing that and defined this algorithm that does it for, as I said, 20 years now. However, this SFMR has been impacted National Hurricane Center forecasts on regular basis, but around 2018, we started getting questions from the field. They felt that in most extreme winds, the SFMR measurements are too high. At first, we did not believe that something with the instrument was wrong. The prevailing hypothesis across community was that physics model used to convert microwave measurements into winds was insufficient, particularly in heavy rain and extreme conditions. So we did what scientists do. We refined the model. This is an example how the downscaling of the retrievals was adjusted in order to provide better estimates for National Hurricane Center. However, when they tried utilizing that, they noticed that sometimes this worked, sometimes it didn't work. IRAP came to the rescue. We've been flying IRAP for over 2 decades, but it was only in 2021 where we equipped the processor to provide the Doppler wind profiles and surface wind measurements in real time in 2021. Comparison from 2022 hurricane season with the SFR winds identified that in some cases the winds are higher than IRAP from SFMR, but in other cases they were lower than IRAP. Again, the detective work that we led on was helped by the 3D wind measurements from IRAP. Here we are looking at the Ivor Pass in the Hurricane Lee on September 8, 2023, and the storm reached Category 4. If we concentrate here in the Ivor, you can see how the aircraft shifted up 200 meters due to the very strong updraft as we were flying. And if we concentrate just here on the surface winds, where we plotted the SFMR, you can see the colors really doesn't match the 3D column. If we zoom in and look at the time series, with red, we depict the measurements from SFMR. With blue, we depict the measurements of flight level winds, and then the black is the surface wind from IRAP. What we are noticing here that the IRAP and SFMR are different almost 35 meters per second. At some point, the SFMR is overestimating, but at other point, SFMR is underestimating. So what is really going on? To unravel that, we go into individual profiles from IRAP. The green symbol represents the flight level measurements, the blue star represents the SFMR, and the black dots represent individual profiles from IRAP measurements. You can see that there is nothing within wind profile that even remotely sends that winds should be as high as SFMR was retrieving them. This is the value of having the 3D wind measurements that collect the flight level with the surface level. So far, we only had that from the drop zones, but drop zones, as we drop them, they deflect. They don't fly and land right below the aircraft, so it was very hard to validate these extreme winds and SFMR with just the drop zones. At the point where the SFMR was underestimating, again, the profile is saying that there was nothing that even remotely indicates that should be the case. So something was obviously wrong. And again, we thought that this was the algorithm that's wrong. In 2023 season, hurricane season, we were lucky to fly 2 different SFMR instruments with IRAP, and I color-coded this scatter plot with the different flights during the season. What we are noticing that when we have flown with Unit 2, we have 2 different type of bias dependent error relative to IRAP. But when we have flown with the unit number 1, we see that the performance is different than the unit number 2. This was indication to us that there is more than just the issues with the model that connects the measurements with the winds. So in 2024 hurricane season, to get to the bottom of SFMR discrepancies, we assembled a multidisciplinary team of electrical engineers, remote sensing scientists, physicists, meteorologists, operational forecasters, and NOAA aircraft crew members. Designated experiment to test consistency of performance between 3 SFMR units owned by NOAA. we decided to change units to obtain coincident measurements with IRAP, but also whenever possible fly close to Air Force track because they also carry SFMR and intercalibrate units, or underflight satellites such as ASCAT and synthetic aperture radar for comparisons. I'm going to show you next what we discovered. This is the first flight we took with Unit 2, and what we are seeing here is basically the linearly dependent bias with increased wind speed. When we change this unit to Unit 1 on the next flight, what we noticed, it was really strange. We are seeing the bifurcation of the scatter plot that was not observed with the first one. And then with the third unit, we get something that resembles kind of constant bias. At this point, we are thinking that Unit 3 is the best unit, so we decided to fly to the rest of the season and try to recalibrate. In order to recalibrate, we designated this experiment where we underflew ASCAT scatterometer and compare all three measurements. The green line represents IRAP, the black line is ASCAT, and the red line is SFMR. As you can see, what we originally saw with IRAP compared well with AirSCAT, but SFMR did not. We attempted to recalibrate, and we did that. We got the better results, and we thought, okay, the calibration is the issue. We continue flying this unit in the hurricane Helene. And the first flight, we see the constant bias that we got used to. But the second flight and third flight showed us that performance of this unit was changing from flight to flight. When we discovered the possible errors, we were really stunned because from forecasting perspective, this meant that they really should not utilize these data for any decisions. The errors were not small ones. We were painfully aware that we need to re-examine entire 20-year database and all other measurements and decisions SFMR data might have influenced. It meant that some measurements in storm force conditions were wrong, and we faced a choice: continue or stop data dissemination. That was not an easy decision, but that moment, as uncomfortable as it was, is where storm force errors begin to turn into golden science. We did stop the dissemination, and I say it turned into golden science because science isn't golden when it's convenient. It's golden when it's tested, challenged, and strong enough to correct itself. The most challenging scientific problems, I believe, are not the ones that are obvious. They are subtle biases hidden inside systems we trust. As we were going and examining further what is happening really with the SFMR instruments, we understood it's not just the algorithm we are utilizing. We noticed the changes in the calibration loads with temperatures through different flights. We noticed that bifurcation that was observed with IRAP with the Unit 1 is indeed correlated with the temperature, thermistor temperature that is installed on the SFMR. We have also noticed that for Unit 2, we had a frequency drift. What we are observing here, that the frequency at the channel 3 that should be under, which is depicted by red color and should be under purple and brown, is above them, so something's wrong. All these frequencies are not changing with the winds, they are just drifting with time during the measurements. So the question I asked myself, what did we do wrong? Why didn't we discover this earlier? And the reason we didn't do it is because how we are used to validating instruments. We have operational requirements that we try to show that these measurements adhere to. For SFMR, that was 5 meters per second. If we congregated all the data, this is with sondes, we get RMS error that is less than requirement. If we aggregate all the IREP data and look at the error, we again get error that is much less than the requirement. What were we doing wrong? The wrong was congregating all measurements together because that masked instability and inconsistency issues. If we separately look performance per flight, and these linear lines are basically fit for different flight days, you see that every single flight is different. So what are the lessons that we learned from SFMR? Is that independent calibration and validation oversight is critical. This was given to vendor, and vendor did validate and calibrate every year, but how was that done was not checked. Appropriate subject matter expertise is not negotiable. It's only when we created a larger team that we went somewhere. Robust methodologies matter. Verification data sets need to be verified too. Cross-instrument consistency must be enforced. And system performance monitoring reduces the risk. None of this has been done properly for SFMR. So where are we now? We assembled multidisciplinary team that includes the SFMR vendor. We returned instruments to the lab. We designed the comprehensive test of experiments to evaluate the performance of each simple component of the instrument. We determined that certain hardware components require replacement, and we updated the CalVal protocols before reintroduction into operation. But before anything returns to operations, it will need to go through updated, more rigorous validation protocols. Now, this brings me to question, how do we preserve gold science standards in the era of expanding data and measurement volume? SMMR forced us to build this framework under pressure, and we did. We were up to the task. The real test wasn't just technical. It was about responsibility and rebuilding trust. What if this level of rigor wasn't event-driven? What if we were to institutionalize it? What I realize is that while we were hardening one system, something else has been accelerating. Satellites are launching at an exponential rate. Commercial providers are reshaping landscape. AI is accelerating how fast data moves into models and decisions. We are building the largest Earth observation enterprise in history. But here is the question. Are we building the infrastructure to guarantee its integrity? What I'm showing you on this slide is number of satellites that were launched by commercial sector depicted by the orange color from 73 to last year, and the blue one is the satellites launched by governments. You can see exponential rise. What does that mean is that as the number of satellite and observation is exponentially rising, the need for calibration and validation will rise exponentially too. If we want golden standard science, science that informs policy, protects communities, and stands the test of time, we must institutionalize trust in data. Not as an afterthought, not as a project, but the core infrastructure. Because in the coming decades, the difference between noise and knowledge, between data and decision, or between uncertainty and actions will be trust. So in order to understand how do I approach this problem, I go back to my hurricane flights. And I was thinking, what did I learn first on those flights? On that first flight was that I need to eat properly in order to survive it. That day, I had a peanut butter sandwich. Now we are much better equipped. I want to use this food analogy to explain what we are dealing with. I want to use the example of farm-to-table approach. So what do we have on farm-to-table? We have farm, we have kitchen, and table. If we go to the farm, we can get raw food ingredients. It's something that comes from the ground that we nurtured and know exactly its ingredients. We can purchase semi-prepared ingredients, or we can purchase fast food. So what happens when we bring these ingredients from farm to the kitchen? We first quality check them, we prepare them, we find the recipe we want to execute, we start cooking. As we are cooking, we are tasting, does it need more salt, does it need more water, or something else. Once we are satisfied, we plate and then we deliver to the table. So what is it that we have on our satellite farm? We have US government satellites. We designed those satellites. We completely understand each component. We have partners, satellites and instruments. We understand them, not to the degree as our government wants, but we do have better understanding. And then we have commercial sector, from which we don't really have the full insight of how these instruments are designed or how they derive the product. So what happens when they come to the kitchen? In the kitchen, we first inspect ingredients. That's an initial calibration and validation we perform. We then prepare the data, we format them for the algorithms. What are our recipes? Algorithms are our recipes. As we are cooking, we are fine-tuning the algorithms. We are performing calibration and validation of the algorithms. We are producing the products, and we are testing them. We are performing the calibration and validation, and this is the process, the circular process that happens until we are happy. Then we plate them. Our plating is formatting for the application requirements. The final test is application, calibration, and validation before we deliver them to our customers. What I want to show is that calibration and validation happens at 4 different stages during these systems. As more ingredients enter the system, especially from the commercial sector, each provider may have their own kitchen. But what we do not yet have is shared, transparent, cross-section certification kitchen, one that ensures comparability, traceability, common standards, and transparency. That is our gap. That's the gap we need to solve. If we treated the data the way we treat aircraft, for example, not every airplane is built by the same company, but every aircraft that flies today meets certification standards. What we need to understand that we certify the aircraft, not the companies that made them. Because certification infrastructure exists, this works. What I'm proposing is not a new regulator. What I'm proposing is National Satellite Data Certification Center, which is federative CALVAL framework under which government agencies, independent Calval labs, nonprofit, and academia all perform important Calval work, but under the standards that are documented, traceable, and understood. What we are lacking today is an authoritative umbrella that ensures that long-term monitoring, transparent uncertainty qualification, and standard tests are executed. They do understand, they do exist, but they are not enforced. Certification tiers, I'm proposing the four tiers, signal the confidence. And I believe that UCAR would be ideal organization to lead this certification center. UCAR is not a vendor nor a regulator and is uniquely positioned to host such an umbrella. UCAR have long-standing relationships with the governments and commercial sector and well-developed models and testbed that can be utilized in this certification center. For the standard certification, I define meta standard that relies on two stages. Stage one, that is scientific rigor, that follows the methodologies utilized for calibration and validation data sets, provides documentation and traceability. And that stage one asks basically the question, is the science rigorous? Are the Calval methods and data sets documented and traceable? The second stage is operational utility. And that stage asks, does it actually work in operations? Does it improve data assimilation, decision support, on mission outcomes for a defined use case? You don't certify operational utility without scientific rigor. To summarize maturity of different data products, I propose 4 different tiers. The tier 1, the browse provisional, is discovery tier, where the new data sets become visible and traceable. They are early, but we allow them to come to the market. The second tier is scientifically sound, validated methods, consistent performance has been established. The third tier, platinum, or I call it certify, shows early operational impact. The data products are ready for operations and they were tested in defined use cases. And finally, the gold standard tier is the full certification. The data sets was independently verified, operationally demonstrated, and is stabled across regimes. The key advantage of this system is modularity. New measurements, like in the early ones in tier 1 and 2, have opportunity to start playing early in the market and advance progressively as evidence accumulates. This gives us both speed and discipline. Certification aligns incentives, rewarding rigor, accelerating adoption, and strengthening trust across the ecosystems. It's giving a market signal to commercial companies that can sell at scale and to buyers that can buy with trust. And trust does not happen automatically. It is built, it's measured, tested, and certified. That is how we turn storm force errors into gold standard science. And that is something worth building together. Thank you very much for listening.
Thank you, Zorana. That was an awesome talk, and what a brilliant idea. Um, Now we will begin the Q&A portion of today's seminar. I'd like to direct everyone's attention to Slido to ask your questions. either the QR code or the tab in the upper left corner of your screen. And while you are doing that, let's see. While you are doing that, I would like to invite you to check out our webpage, CPAESS.UCAR.edu for upcoming seminars. Our next scheduled seminar is on March 4th at 11 Mountain Time with Dr. Bao Zhang, CPAS scientist at GFDL, and he will speak on how predictable are North American summer heat extremes on the subseasonal timescale. We also invite you to find this talk and all past talks on CPAS's YouTube channel. Okay, so while people are getting their questions together, I had a couple of questions for you. First of all, the content of your talk is amazing, super practical and important. Just because, as you mentioned, the market is getting more and more flooded with data sets, and we just people need to know what data is going to fulfill the purpose that they have. And certainly we see this across all kinds of industries, like a neutral standard that's showing what things can be used for what. But before we get into that a little more, I just had to, because you've flown into hurricanes and almost no one has done that. Can you take just a couple minutes to say what it is like when you're, I really appreciate the video. Can you tell us what it's like flying into a hurricane?
It depends from storm to storm. Sometimes the category 5, when everything is steady state and stable, and much easier than the tropical cyclones or tropical depressions. But in general, it's turbulent. It's a dark, and we are all hanging on until we are passing through the eye wall. I am very concentrating and monitoring on data we are collecting. So I'm not the one taking those movies.
Right. And then before you've told me that once you get into the eye of a hurricane, there's all these beautiful clouds around and it is kind of calm. Like people use it as an adage, but they've never experienced it.
It's really breathtaking when you get to see that stadium, view of the clouds. I saw it both with the moonlight and the sunlight. Yeah,
Wow.
um, that with the moonlight, it's really something. It's something special. Um, Going through the eye wall and then meeting this calm eye is really breathtaking. And I do always take a moment to just I don't want to say enjoy, because each moment, right, when we are there, we are collecting data, and that calm is a data point as well as the violent part. But there is something, yeah, there is something special when
How
you see it. It's not always that organized. Sometimes we don't see it at all.
Mhm.
Like the eye, it's very rugged, and you don't see the very begins or very ends. Um, but yeah, I mean, few times, more than few times, I was actually lucky to see it.
Wow. How cool. And how wonderful that you are uh, the woman who has had more eyeball penetrations than any other person, any other woman on the planet. How amazing. That
I
is
was
just,
hooked and I stuck with it.
it's just
When I
amazing.
believe in something, then I stuck with it. Yeah.
Okay, so to get back to your talk, and I know you covered this, but just to kind of like re-say it for people who don't fly into hurricanes like me. Uh, so certain data sets will give you good information. Other ones will give you information that might be misleading because they're better suited for other purposes. Is that correct? Could you give me a little more information about that?
Do you want me to go back to a slide, or
Sure,
we
sure.
have multiple let me find. We have a multiple instruments on board on P-3 aircraft, and they all provide different type of information. I'm trying to see. Yeah, so the one that my team flies, IRAP, which is double frequency Doppler radar and scatterometer, is simply, I'm not saying it's better than the other ones, but I'm saying it's providing more information than the other ones because it's connecting the measurements from the flight level to the surface. It's providing the 3D, so the atmospheric winds in the profile as well as on the ocean surface. We have the flight level instrument on board of P-3 aircraft that provides these measurements at the flight level. This is just that line here, right? And before IRAP, what NHC had were drop zones. These are these lines. These are measurements of the atmospheric winds as the drop zone falls from the aircraft. But you can see even here how it deflects from the aircraft track. So if you want to compare the wind here down here with the surface measurement from the drop zone, there will be some difference, right? Because drop zone didn't land here, it landed somewhere else. But IREP is providing us additional measurement right here, right below the aircraft track. That coincides with the SFMR measurements. What SFMR is providing is winds along this line. So what each measurement, when it's remote sensing instrument, each measurement will have some type of errors. When we can understand those errors, then it's easy to use those measurements. The problem is when we don't understand them and we didn't define them well. We thought for many years that we understood the SFMR. But we thought that because we didn't have anything else to compare it with but the drop zones.
Excellent.
When we got the new type of measurements, right, in near real time, we started realizing, oh, something might be wrong, right? We were given those questions from National Hurricane Center because they compare not just aircraft data, they compare every single data set that comes their way, right, to make decision. They started noticing that something just doesn't add up. But the problem was it wasn't always the case. So
Mm.
they couldn't really know when to trust it and when not, right? And
Yeah.
because the instrument was calibrated by vendor every year, we thought that that was taken care of.
Mm.
But the government did not independently check whether those practices were right. In our team, we did notice that something was off, and we actually had the recalibration routine for SFMR, but we assumed that the frequency with which we are taking measurements follow the physics. In other words, they are spreading as they should. That wasn't the case. And we, like over the last several years, realized that. And now that we are performing lab tests clearly are showing that every one of these three instruments was different. What I didn't say is that Air Force have 20 SFMR instruments, but they do not have IRAP to compare it with. With the new matrices and tests that we defined, we are noticing that all of them are different too. So something needs to be done.
Yeah. We do have some questions for you. Um, in your view, how open are commercial satellite companies to collaboration on data standards, quality certification, and the other issues that you raised? Thank you, Matt.
They are very interested. I've been talking about this idea for last 6 months in earnest, and especially commercial companies, their biggest issue is when they try to sell data at NOAA, and I worked on 2 pilot projects from commercial data program, is that they don't really understand what we want from them. We don't have clear um, standards for data. We have these mission requirements, and it's very easy to use the data set, flag it certain way, and to prove that you are meeting those mission requirements. But when you examine data sets from multiple perspectives, then you start understanding that cannot be used in applications. So we've been going back and forth with different commercial companies, and they clearly understand that if we have this standard and we connect the price with the tier level, then we can buy at quality we need, and they can sell for higher price, right, if they have better product. We had one issue when 2 companies were trying to sell us data, and one had higher quality, the other one had lower quality, but no, I wanted to pay just flat price. Well, as you can imagine, the company that invested in quality wasn't happy about that, and they shouldn't have been. They actually invested in quality. Why wouldn't we reward that? There was a company in Australia that I met a woman that acquires measurements for certain type of applications, and she told me she pays 5 different companies to provide the validation data, and because of that, she charges her data higher. But she doesn't have a way to document that's why her data is better. In my proposal, I divide tiers based on how many data sets were used for verification. In essence, maturity of data sets will be lower if just one source was used to validate versus if multiple sources were used to validate. And she absolutely loved this concept because it would give her opportunity to show to the customers independently that her data is better than some other products. Hope I answered the question.
I think you did. That's great. We have another one. The Meta standard certification you proposed makes sense and is excellent. The SMFR data, if SMFR data were to go through the certification process, would it be stopped at the bronze status? Thank you, Laing.
So what the problem with SFMR is that doesn't meet specifications. What we did, we utilize all the standards necessary for the highest certification, but what didn't pass is the quality test. So when I'm saying the performance rigor, right, in stage 1, is that that stage defines what type of matrices we utilize, defines what data sets we utilize for CalVal, but it also looks whether the performance, which is outcome of these tests, meets requirements, right? Not just mission requirements. And what we have shown with SFMR is that when we pass through all these tests, every single flight was different. So it doesn't pass the performance score. And right now it shouldn't be used in operations. So it wouldn't get any certification as is right now.
Thank you so much, Zorana. I think it is noon right now. Zorana, can you share with us your email address in case anybody watching this live or the recorded version has more questions to follow up with you?
Yes, how do you want me to share?
You could just say it unless you.
Uh, that Jelenak at UCAR.edu.
Okay, excellent. I just want to thank you so much for your presentation, and thank you to everyone for coming for the to the UCAR CPAS Discovery Seminar. And remember, you can go to our website to find this talk and future talks on cpass.ucar.edu. And then you will be able to find this talk once it's uploaded onto YouTube. There'll be a link there. Zorana, our sincere thanks to you for sharing your important work with us. I really hope this is able to come into fruition because it is a brilliant idea and one that is truly needed. Um, Thank you also to Alex Meyer of CPAS and Fletcher Ryan of UCAR Multimedia for their invaluable assistance. I hope to see you all at our next CPAS Discovery Seminar in March. Have a good afternoon, everyone.
Thank you for the opportunity. I appreciate it.
Thank you.